Hello everyone, this is lecture 4 of PTRE 475575. Well completions and advanced stimulation techniques. Today we will carry on with module 1. We got a little bit deep into some mathematical subtopics in the previous lecture. One thing I want to say, I did update the slides, mostly to fix some small typos that existed here and there. But on the slide that we were talking about the Young's modulus, and it must be the last slide we saw. So let's start from there. I made a small change that is technical, but it's not going to be a very big difference. So we had this cube, and we apply extension stress somehow. It has cross-sectional area A and height h. And because of this stress, extension stress, it becomes, basically it's Hooke's law, it extends by about delta z. Now, what I had before, so basically, I had it was correct what I had. It's just, I think it's better if I present it this way than what I had before. Let me use a neutral color ink because there is so many colors into this. So this is the force I applied to get this extension. So according to Hooke's law, this is true. And you learned that in high school even. So if this is true, basically, I think in high school the way they did it was like Fz equals K delta Z. So you replace this with this, right? So that's fairly simple, and that's exactly what we are doing here, with the exception that we divide this by a constant A, and we divide this by a constant H. Because they are constants, they don't mess up the relationship of proportionality. Okay, what is on the left is proportional to what is on the right. They are proportional to each other. So if I divide by a constant, it doesn't make any difference. Okay, that's exactly what is happening here. And what I did is just I elaborated it more technically. I replaced the proportional sign with equals E. And what is E is basically the Young modulus, which is also known as the modulus of elasticity. Is a quantifiable measure of the stiffness of a solid material. The stiffer the material, the more force you need to apply, the more stress you need to apply to generate a fixed deformation. That's about it, fairly simple. And I think you should already be familiar with this from geomechanics. Shouldn't be that bad, easy. Now, as I said, if we have two materials and we agree that they are both behaving in a linearly elastic fashion, okay, material A and material B. Material A has low stiffness, low Young's modulus. Material B has very high Young's modulus. Okay, I don't want to give examples, but imagine one of them is like steel or something. Imagine how much stress you need to apply to the steel to get a minuscule extension. And the same extension with the other material, the more less stiff material, you can get it with a much smaller stress. Now, a good question here would be, and I heard that in a PhD defense in a different university, and it was a very good question. It was, what is the antonym, what is the opposite of stiff? And the student was talking about rocks, obviously. He said soft. It was a Chinese student, I believe. It was a student who didn't speak English as the first language. And he said soft. And the professor in his PhD committee that asked him that question, he said, no, it's actually complacent. And actually, if you go to a lexicon and dictionary, you will find both words as antonyms of stiff. But for our purposes, complacent is the technical term of something that is, I guess, not stiff, the opposite of that. Now, similarly, as Young's modulus is the stiffness measure, there is also an inverse of that that is not very well used, and we have seen it in geomechanics. It's given by C, and is the complacent modulus, something like that, something similar, but the opposite of Young's modulus. But generally speaking, Young's modulus is what we are working with in this kind of situations. So if I tell you, for instance, oh, in China, they want to fracture the rocks the same way that we fracture them in America. But unfortunately, in China, the rocks are deeper and the Young's modulus are very high. That means to create the same deformation in the rock in China, you need much bigger stress than in America. Okay, and therefore that would translate into you need more frac pumps, you need a bigger frac fleet, etc., etc. That's what it translates to. So one important thing is that delta Z and FC, notice they were both in the same direction. Okay, I wasn't applying stress in the Z direction and getting extension of the X direction, right? So that is important. It's a uniaxial modulus. And mathematically, in mathematical terms, it needs to be sigma II divided by EI epsilon II. Okay, I can be direction, IJK can be XYZ, as long as the indices, not the indices, what do we call them? I forgot the name, not superscript, subscript, are the same with each other, I'm good, and the same. So I apply stress in the I direction, I get strain, i.e. deformation, in the same direction. Okay, this is exactly what Young's modulus is telling me. And it's very easy to measure the Young modulus in the lab of a material. You put the material, measure its height, put a weight on top of it, measure its new height. It should be shorter than before. So it's opposite of the problem that we saw in the previous slide. It's not an extension, it's a compression, compressive stress that you apply. So you put the load on it, you measure how much it shortens, you divide by the original height, and then that number, you divide that number, you take that number, and you find the weight of the stress of the load that you put above it, you divide by that shortening divided by the initial height, and you have the Young's modulus, basically, in units of stress or dimensions of stress. The solid will most likely shrink in the direction perpendicular to the applied stress. Now, this is going back to the previous problem of extension. It was height H, I applied stress or force Fz over the cross-sectional area A, and then I got extension delta Z. Okay, now, yes, the material becomes longer, but at the same time, it would become slimmer, right? Most likely. It would become if it becomes longer like this, it's going to become slimmer. And the slimming, let's say, or the thinning will be in a perpendicular direction, right? It would be something like I apply, it was something like this. I made it longer, but I will also make it thinner. It will become thinner at the same time. Okay, now let me take, we talk about the strain in the direction, say in the z direction, it would be basically E z z is delta z divided, it was something like delta z divided by h. That's the strain, okay, dimensionless. But let's just say that this was the x direction, and this was the z. So x would be, oops, sorry. I will have a delta, a new x, basically, let's just say x prime, and the original x was x. So the strain in the x direction would be something like x minus x prime divided by x, which is also directionless, right? X was the original width. X prime is the new width. Say it was 10 and now it's 8. So x minus x prime is going to be 10 minus 8 is 2 divided by 10. So the strain in the x direction would be, what, 0.2, something like that. Now, I didn't intend to create the strain in the x direction. I got it sort of indirectly by triggering the strain in the z direction, right? So it became, in the z direction, I went from h to h plus delta z. And then in the x direction, I went from x to x prime, let's say. Okay. So actually, I have a mistake here. I should be x prime minus x. So it would be negative. That's what I was going to say. Yeah, I called it x minus. So it would be minus 0.2 because I became taller but thinner. And the opposite is possible. I can become shorter but fatter. You know? Now, it's important that those two are not the same. They don't have the same side. Okay? One becomes taller, the other one becomes fatter. Thinner. One becomes shorter, the other one becomes fatter. So they work against each other in a sense because one is induced by each other. Now, if I take those two and I compare them, this is basically what I have here. Epsilon J is what the indirect one. What was epsilon XX in the what I was drawing, and the epsilon II is what used to be epsilon ZZ. Okay, and we said one is positive, the other one is negative, and I accommodate for that by a negative value to make it positive. So I have what we call the Poisson's ratio given by the Greek letter mi. That is basically what on the numerator is what I indirectly cause, and on the denominator is what I actually cause. So I went for epsilon ZZ and I got epsilon XX. Okay, something like that, something along those lines. I wanted to do one and I got the other. Okay, now let's see. For the rocks, the Poisson's ratio will vary from 0.4 to 0.1 ish. 0.4 is a little bit high. 0.1 is not impossible. Your TA Kalu is doing experiments in the lab using transparent gelatin blocks, and those get close to 0.5. Get close, not exactly, yeah, like 0.47, something like that. You get close to 0.5. But you cannot go over 0.5. If you go over 0.5, it means that you are violating the laws of thermodynamics and the laws of physics in general. You are getting more energy out than what you are putting in. So it's impossible for Poisson's ratio to be bigger than 0.5. But it's possible for Poisson's ratio to be negative. You can have a material that gets fatter and taller at the same time. It's called foam. It won't be wrong, it will be foam. Yeah. Foam. Okay. Any questions? Okay. That's about Young modulus and Poisson's ratio. It's the easiest of those 6 moduli to conceptualize what they work for. But every modulus has a physical meaning. It's just for those 2, it's easier to understand what we are talking about. Okay, yeah, 0.1 to 0.4. Don't go over 0.5. If you measure something, pinch yourself that is over 0.5. We had a student that he went and put a poster in, not my student, in geomechanics conference or symposium saying, I measured my material, I made some synthetic material, I measured it, I put it in the autolab, I measured the Young's modulus, so the Poisson's ratio, it was 0.7. I was like, okay, it doesn't mean that if the autolab, which is a $2 million cell, testing cell that we have here at the University of North Dakota in our facilities, it doesn't mean that if it says 0.7, it's 0.7. Okay? The autolab is telling you what it's measuring. Okay? It doesn't mean that he was being advised by somebody outside of the school and the person only cared about getting his name on some paper. So he told him, put your results in a paper and publish it so that somebody will take it and cite you. And then basically this person will go and tell his boss, I had somebody write a paper, give me a promotion. These are not smart stuff to do, but happens, unfortunately. Anyway, ultimately what happens is that this was a multi-layer material, and the way it was deforming, one layer was pushing the other underneath it. So it was appearing that the material as a whole has Poisson's ratio bigger than 0.5. No, it behaves. It's an apparent measurement. It's not a real measurement. It doesn't mean that the material is 0.7. So need to be careful with this. Yeah, always pinch yourself if you are measuring over 0.7. Now, the real behavior of rock will deviate from linear elasticity. You have anisotropy, we said with direction, change with direction, and heterogeneity, changed with location, region. Often rocks are not perfectly parallel or contain microcracks. Both these features make the initial stress-strain behavior appear less stiff than the actual stiffness. After this, the rock may display a linear response, a good point to calculate E, followed by softening while approaching its peak stress, UCS prior to failure. Now let me tell you something. Let me explain what do I mean by this. If I have a material that has a lot of cracks in it, it has a lot of pre-existing failure plates or in it. If I start compressing it, it will, those micro cracks or whatever are gonna close first, okay? So initially I apply a small stress, I get very big movement. I get very big strain for the stress I'm applying because there are micro cracks that are closing down. So the material is not fully solid. It's solid with some defects, and those defects. And some of those defects are making the material misbehave. It appears that it's softer than what it really is, okay? Because I'm basically creating motion or deformation by closing those micro cracks. Closing the micro cracks, I'm not compressing the actual solid. I'm just like compressing air out of those cracks and closing them down. You know? So if you're doing experiments, don't believe what the machine is telling you or what even what the data is telling you. Think about it. It's trying to tell you something. If you are measuring the Young's modulus, make sure you measure it at a point where the material has already compressed enough that all the micro cracks have closed down. That's why they say, people say, I was a TA, there was another TA who came from a different place. When I was in Texas, I finished my undergrad and then became grad student immediately, and I was TAing a class. And there was another TA that was from a different place, and he said that his professor in the old school of him, he was telling him, you need to be very experienced to get those values, good reading of those values, even if it's a simple experiment. And I didn't really believe him. I didn't really understand what he meant or agreed with him, but now I realize. Example problem number 2. A 100-pound force load is applied on the cross-section of a cylindrical core sample of a 1-inch diameter. The core's initial length is 2 inches, and the load application reduced it to 1.75 inches. Calculate Young modulus of the core sample. This is a very simple problem, actually. You have a core. It's 2 inches. I apply a stress. What is it, the 100-pound force? And then the result was that I compressed it, became shorter, sort of became 1.75 inches. It was compressed. I'm shorter than what I was before because of the 100-pound force above me. So what will happen is that, okay, what is the stress? I want the Young modulus, so I want the stress divided by strain. Now, let's just say that this is the z direction. So it's basically sigma zz divided by epsilon zz. Very simple. So what is sigma zz? Is the force divided by cross-sectional area. So it's 100-pound force divided by, what is the cross-section of a core? It's pi r square or pi d square over 4. It's easier to do pi d square over 4 actually due to the numbers that we are using. 1 inch square divided by 4 inches squared. So the result is 400 divided by pi pound per square inch PSI. Okay, what is the strain? Strain is the change in the height, which was basically the delta z, which is 2 minus 1.75, or more like the other way, new minus old. So it's, but it really doesn't matter for this, because if you do it properly, you are gonna do it 1.75 minus 2 divided by 2. So you have minus 0.25 divided by 2. It's a negative value of minus 0.125. The thing is that if you want to do it this way, the force is also negative, must also be negative because it's pointing down, right? Unless I assume that z is positive when going down, and then the strain will be positive too. So those two have the same sign ultimately. So it's better to do plus and plus. But anyway, Young modulus is basically 400 divided by pi divided by 0.125. And then 0.125 is a fraction that I don't. Anyway, I think I have the actual answer in the slides. Yep. Uh, 1019 psi or 1.9 ksi. Same. Now, any questions on that?
Would it be 1.09 KSI?
Yes, should be 1.2 or
Oh, sorry, yeah, 1.02.
Yeah, you're right. You're right. Sorry about that. Thank you. 1 point. Yeah, we remove. So 1.02. Yeah, we'll fix that. And also check me on the. I might have having mistake on the calculation as well. I don't know. Anyway, so example problem number 3. Now, same problem. The material, the core became shorter, but it also became fatter. Okay, it increased its core diameter to 1.031. It was 1, it became 1.031. So calculate the Poisson's ratio. So now we said I had, well, this was the core. I compressed it, became shorter. Well, let me draw it, but it should become fatter as well as shorter, but also fatter. And I'm exaggerating here a little bit, but it was 1. Now it's 1.031, and it was 2. Now it's 1.75. When I do the Poisson's ratio, I don't care about stress. I care about strain I induce indirectly divided by strain I induce directly. The direct strain, what is going to be in the denominator, is that 0.125 that we talked earlier. That is the epsilon zz. The epsilon, if we say that this is x, the epsilon xx or radial, whatever we want to call it, epsilon RR, it's gonna be, well, at the bottom I have to have negative. At the top I have, it was, now it's 1.031. It used to be 1 divided by the initial, which is 1. So it becomes 0.031 divided by 0.125. One is positive, the other one is negative, so I have the negative sign, which should be something like, let's see, 0.248 units. And that's when I check myself, is it between 0.1 and 0.4? Does it make sense for a core? And the answer is yes. 0.25 is a logical Poisson's ratio for rock. Okay. Example problem number 4. Using information from the previous 2 example problems, calculate the remaining 4 moduli used for modeling the core sample stress induced deformation behavior, considering that it honors linear elasticity. So I calculated in the lab 2 moduli, Young modulus and Poisson's ratio. I want you to give me the other 4, as we said earlier. So I take that table from the previous slides or my homework from geomechanics and the spreadsheet, I guess, I created in the homework, and I just calculate those values. This is the bulk modulus, which is the inverse of compressibility, actually, 680 psi. Lame's first parameter, lambda, 408 psi. Shear modulus, G, also 408 psi. P-wave modulus, or Lame's second parameter, as it's often called, 1223. So once I have those 2 values, everything else is plugged in the calculation. Becomes very, very simple, very, very easy. And then I have all 6. So now you can tell me what anything about the model in terms of stress and deformation, assuming that we already agreed that the model behaves linearly elastic. It can be a very complicated model that I need more information to give you this stuff. 2 measurements are not enough, and we need to go further. Could be, but for linear elasticity, this is the case. All right. Any questions? Because I'm gonna shift gears into a different subtopic. More applied, actually. So we're gonna go back to Anderson. And we said Anderson made our life simple by telling us, forget about S1, S2, S3. Let's just say one of them is very vertical, the other 2 are horizontal, and you call the vertical SV, and the horizontal, the bigger of the 2 SH max, the smaller of the 2 SH min. That's it. He made our life mathematically extremely simple. But, okay, no, a good thing. SV is often called the overburden stress. Ultimately, what SV is the mass of the rock above you. The stress exerted by the rock mass above you. I'm basically asking you, if you want to give me SV in this location here, at this depth, just calculate the mass of the rock above this location, this depth. That's all you have to do. It's a very simple problem, but it's not easy to calculate. It actually has, within structural geology, if we call structural geology a sub-discipline of geology, there is a sub-discipline, there is a specialty called overburden estimations. And people have tried to do that. I think Richard Schultz, who was teaching geomechanics last semester, has done overburden estimations for NASA at some point for a different planet when he was a postdoc or something. Like there is, or even for the Earth, there is a lot of people working on this and on this topic. I don't know how well paying that discipline, that specialty is, but basically what you are doing, you are solving this integration somehow. We will simplify it and solve it mathematically in an easier fashion, but this is what we really solve. We basically want to divide the rock underneath us in layers or above the point of interest. If my point of interest is 7,000 feet, I have 7,000 feet of rock to worry about and measure its mass. Let me divide it into different layers, or if it's already composed of layers, okay, take the density of each layer and its height. That's all I need. And I add it up together. I multiply every layer, its density with its height. And then I add it all up. And I get a big value in PTRE. Now, there is two ways you can do it. And when I'm doing geomechanics, I always pay attention to that because it's rho G delta Z, which is basically rho GH. Rho is density, pound mass per cubic feet. Z is length, feet. What is G gonna do? The answer is that G is gonna convert the pound mass to pound force. Or if you are using SI units, it's gonna convert kilograms to newtons. Okay? When you are using SI units, this G really matters because you want to go like 1 pound, 1 kilogram is exerting 10 newtons, right? So 9.8 newtons, 9.81. So it's a real thing. That G is real. You need to include it. But if you are using American units, field units, a pound mass, how much force does it exert in atmospheric conditions? 1 pound mass exerts 1 pound force. Okay, I don't need to change that. So if I'm 200 pounds, I'm exerting 200 pound mass. I'm exerting 200 pound force on the floor where I'm standing. Right? So I don't really need G. I can take it out. Now, what happens many times is a sad thing. Took me a while. The good thing is that I got like confused about it as soon as I came to the US, and then I fixed it. I got it sorted out in my head early on, so I didn't have that issue later. But I find out some people have this issue later on. Is that if you go and Google what is G in American units or oil field units, whatever you call it, and you find a value 32.2 feet per second square. Okay. Then you take this and you put it in the equation as actually 32.2. It's like assuming that 1 pound mass exerts 32.2 pound force, which is not true. the American units are automatically converted from mass to force. You don't need to multiply by anything. So if you are using American units, just take the G out of the equation. Pretend that it doesn't exist. Now, in real life, for the depths that we are interested in, something like 23 megapascal per kilometer. Every kilometer depth, I get like 23 megapascal wave. That's the typical, what we call the lithostatic stress gradient, which translates to roughly 1 psi per foot, which is an easy value to remember. And I'm expecting you to use it as a rule of thumb. If you don't have any information, you can use 1 psi per foot. If you don't have any information about the overburden in this location, use psi per foot. 1 psi per foot. That's how much the Earth weighs on average. This is a rule of thumb, which is basically an approximate, an easy solution I can approximate. Now, for fresh water, it's a fixed value. How much does fresh water weigh? 0.43 psi per foot. Every feet in depth, I get 0.43 psi above. This is roughly 10 megapascal per kilometer, or 9.8 to be more exact, 9.81. This is not a rule of thumb. This is an actual value. We call it the hydrostatic pressure gradient. Now, lithostatic comes from the Greek word lithos, ancient Greek word for rock. The modern day Greek word for rock is petra, like petroleum, the oil of the rock. In the ancient times, they used to use lithos for the rock, so we say lithostatic stress gradient. Now, hydrostatic comes from the ancient Greek word "hydor," which means water in ancient Greek. Unfortunately, in the scientific community, when you hear the word hydro, it might mean fluid, it might mean water specifically. So when you say hydrostatic pressure gradient, it doesn't always mean fresh water. It could be, I have this drilling mat, its hydrostatic pressure gradient is 0.6. That means it weighs more than the water, 0.6 psi per foot. It weighs more than fresh water, but it's like the gradient of that fluid is 0.6. So it's like, you need to understand the context of where it's used. And many times it's used interchangeably, unfortunately. Hydrostatic. Sometimes they may imply fresh water, sometimes they may imply just fluid, a specific fluid. So, what about offshore? Offshore, let me get hydrated. Hydrated means getting some water into it. What about offshore? Offshore, you have sea water above you. Okay, this sea water weighs a lot, and you want to see how much it weighs. It adds to the SV, okay, to the value of SV. So the value of SV is just how much what I have above me weighs, very simple. So need to incorporate the weight of seawater above the location you are estimating SV. Seawater gradient. Look at that Gulf of Mexico. I need to fix all those slides. I fixed earlier. I think I had the Gulf of Mexico. I made Gulf of America. I will be fixing it as I go along. But anyway, the Gulf weighs about 0.465, so more than fresh water, and with about 3.5% salt by weight, more or less, it adds up to 0.465. This is an approximate value. There are places in the Gulf that are more than others, obviously, as you can understand. If you go to a near a desalination unit, the desalination factory adds disposes the salt removed from the water, from the seawater back into the sea. So if you go there, I used to think 2007, I was a lifeguard at a beach in my hometown, and then I used to go there every year. And then I think 2014 and 2015, I didn't go home for the summer. And then 2016, I went back home, and I swam where I used to go and swim, and the water was itching like crazy. It was like it felt more salty than what it should have been. And then I realized they had built a desalination. That's why. They had built upstream of where I was a desalination unit. Obviously, the salt that was added back to the seawater was coming towards me. And I was like, that explains it. Yeah, salt makes the seawater weigh more. That's what I'm trying to say here. And then still you can use the trapezoidal rule. Oh, yeah, trapezoidal rule to estimate SV. And what is the trapezoidal rule? It's basically dividing the overburdened portion of the rock as layers. Layer 1 with this density, layer 2, this density, layer 3. It's just you have an extra layer on top that is the seawater. Treat the seawater as one layer, as layer 1. Now, and then you have this. This is another way of measuring, estimating the overburden. In this way, I'm not given the height of the layer at the top and the bottom of the layer. I'm given the height of the layer in the middle of every layer. Then I'm using this equation. It's the same as the previous equation in the previous slide. Only the previous slide, you have the top and the bottom of every layer. It just depends. They are both approximations. But ultimately, offshore, you need to have layer 1 to be the seawater. Now, it could be, as you go deeper in the seawater, its density changes too. So you need to take that into account as well. Okay, I don't remember if it becomes heavier. It must be becoming heavier. Yeah, it certainly becomes heavier the deeper you go. One common mistake that students do is that they don't treat the seawater as one layer, and then they just add the seawater weight on every layer. So that doesn't make sense. It's like then you're going to have a very high SV value if you do that. It's like I can measure how much the seawater weighs, and then you add it on layer 1, then don't go ahead and add it to layer 2 as well, and layer 3, and layer 4. Then you are over counting, double counting and triple counting, quadruple counting the weight of the seawater. You are going to get a huge value of SV. It's a very common mistake that I was seeing when I was teaching geomechanics. I was like, please don't do that. And this is how we estimate the magnitude of SV, basically. We ask the geologists, the overburden, people who do overburden estimations to tell us how much the rock above this point, this depth of interest, weighs. And yeah, I'm expecting to hear something near 1 psi per foot, equivalent to analogous to 1 psi per foot. Okay, so any questions about how we estimate SV in the real world? Okay, so the next one, SV is the easiest. Next one is gonna be the second easiest or the second hardest, which would be SH mean. Okay, SH mean we don't go to the geologist, we go to the petroleum engineer. It's a little bit more mathematical to do that. It's not terrible. It's not terrible. We do something very often when we are drilling a well. We do what we call a leak-off test. Now, when we say leak-off test, there is a bunch of tests that fall into this family. Mini-frac, extended leak-off, formation integrity test, etc., etc. Actually, formation integrity test is not exactly the same as leak-off test, but all those tests, and you know there is a lot of names. Every company, they have their own sort of way of doing it. There is a bunch of patents that are on those tests. A lot of, how you call it, controversy on how you interpret those tests, etc., etc. I had a friend, well, I know some student in, he's a PhD student and he's doing experiments on rocks, on basically blocks of cement. And he's like, I'm trying to interpret the same results that we do in the field from the lab. And I see those plots every day, and I still don't understand how they work. It's like a tremendous confusion. It can be confusing. It can be confusing when you are doing this test. Now, what is the purpose of this test? The purpose of this test is to see how much pressure the rock can sustain before it breaks. So when we are drilling, we set casing, we cement the casing, and then we are about to drill a new section. So if I drill a new section, what is the location that is most vulnerable to fracturing? And the answer is directly below the casing shoe. If my casing goes to here, the shoe is here, or it would be like this. The shoe is here. This is the, right below it is the location where I can cause fracture the easiest. It's the most vulnerable location. So I'm asking myself, how much can I pressurize my well without fracturing the shoe? And I will do the leak-off test for that. I will basically eject until I see fluid not breaking the rock, but just about leaking off the rock. You are because the rock is porous, the fluid is expected to leak out of the rock earlier than just before the rock breaks. So once I catch that particular point, that's where I have the leak off. That's what I'm looking for during a leak off test. So the idea here is that I start pumping. I want to use a different color. Green. I start pumping. Pressure increases. All good. I start pumping, pressure increases. And then it gets to a point where I keep pumping, the pressure increases, but not as much. I get this deviation in the slope. Okay. I get this deviation in the slope. It starts kinking down. That means I'm injecting, but the pressure doesn't go as high as I'm expecting it. Why is the case? Because the fluid starts leaking into the formation. Now, if I keep going, I will get more and more leak off, and then I will get a sudden drop in the pressure. That's when I have the actual fraction. Okay, that's when I have the actual fraction. But it's a leak-off test. So what I will do is I will stop pumping, switch off the pump. Immediately, the pressure will drop to something called ISIP, instantaneous shut-in pressure. And then it will level off. Excuse me. It will level off, excuse me. Something like that. And then generally we call this pressure here, we don't have it in the, we call it FCP, fracture closure pressure. If you had a fracture, it would close at that pressure. But yeah, now if we see that in a leak-off test, I have this pressure, LOP. What does it mean, leak-off pressure? That's where the slope starts changing. Leak-off pressure, LOP. And then I have ISP right there. And then I have what I told you, we call it FCP, but it's not in this plot here. Those three pressures are roughly speaking equal to each other. They are not very far from each other. And you can have one that is slightly bigger than the other this time. You can have one that is slightly bigger, a different one in a different test. They are all very close to each other. In fact, chances are ISIP is going to be the highest of the two. But they are not particularly different from each other. And I would say, well, I know there is a lot of debate in which is going to be closest to SH mean. But I have seen papers saying approximating SH mean with LOP. I have seen papers approximating SH mean with ISIP. I have seen papers approximating SH mean with FCP. They are all an indication of SH mean. Generally, you have to get the highest one. So for this class, I'm just playing a numbers game with my chances, and I'm telling you ISIP. We'll be calling it the approximation of SH. Just because, but don't be surprised if you read a paper and they use leak-off pressure values data for SH. It's not unlikely. It's not unlikely. But this is how you basically do it. Now, if you are gonna do hydraulic fracturing, we're gonna see it on module 3, but I'm just telling you now. Same process. Same process. Go up. Leak-off pressure. Keep going. Drop. Then if you still pump, keep going, and then switch off, will level off like that. This part here is called unloading, removing the fluid from the well. Flowback. There is companies specializing in doing flowbacks from hydraulic fracturing. Just before I came over here, I used to live in Colorado for a year. I was doing a postdoc, and there was a lady. She was the manager in Texas Roadhouse in Arvada. And I think she told me her husband was doing flowbacks in North Dakota. And he was telling her it's too cold. She's not going to survive in North Dakota. I was like, oh, interesting. But anyway, this is very similar. Now, also a little bit too early to say it, but I will say it. The earliest pressure, if somebody asks you, what is the lowest pressure at which I can get fracture to initiate? The answer is LOP. Okay, and the highest pressure I can get a fracture to initiate. It's actually the highest pressure I will ever see in the well. This is called FBP, formation breakdown pressure. That's the highest pressure the well will ever see. Okay? So if you are trying to test the well integrity, you are looking at FBP. You want everything to work well when the well is at FBP. Now, from LOP to FBP, anywhere from here, pressure to here, all these, they can lead to fractures initiating. Anyway, I can have fractures initiating at any point from leak of pressure to formation breakdown pressure, and it doesn't mean that I will know on the surface that fractures are forming. It's not like the well is gonna raise a flag and say, I'm fracked, stop pumping, you know? Any point there can lead to fracture. So now when I'm talking about fracture, I'm talking about tensile fracture. So leak of test, LOT, shows the pressure, leak of pressure, LOP, at which the fluid starts leaking into the formation. Fracture initiation can occur at any point from leak of pressure all the way to formation breakdown pressure. And yeah, so the whole group is called leak of test. I know Nicolas Espinosa in Texas calls it hydraulic fracture test because the fracture that you are intending to create is basically the same as the hydraulic fracture that you do during a stimulation treatment. I like to be more general, more fundamental. I call it tensile fracture test. Okay, any of those tests, mini frac, extended leak of blah, 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 they all try to get you close to the point where you generate what we call a tensile fracture. And we're going to talk about those later on. Tensile crack. Any questions? So this is how we measure the SH mean, or we constrain its magnitude. But there is lots of ways you can skin the cat. All of them are effective. There is several ways you can run this leak of test. So several variations. I have a drilling book that I use for my other class, advanced drilling. It's a very important book from 1978. I forget the title right now, but it's important. And it's like oil well, drilling, engineering, something. But gives you 3 ways of doing the leak of testing. One is by observing the way the surface pressure increases with pump strokes, so constant volume pumping, or time, i.e. stepwise increases in pressure or volume. So let's some screenshots I took from that book. Sorry. Here, you pump strokes with the, the pumps are measuring, drilling pumps, the mud pumps are pumping strokes. And you see how the pressure increases, and there is a point where the pressure stops increasing. Even if you pump an equal number of strokes, every stroke is a fixed volume. Once you stop increasing, the pressure stops increasing, that's where you get the leak off. You can do it in increments in terms of time, and then you're going to see those steps. And then when the steps lead to lower pressure, when you start losing pressure from the well, that's when the leak off happens. Or you can do it in terms of constant volume, like every time you inject a fixed volume, say a fixed volume increment, and every 5 minutes I pump this amount of gallons. And then again, you're going to observe the pressure dropping, there will be a point where you put fluids in the well and the pressure doesn't rise as is expected to. That's because the well is leaking out. It's leaking out, it hasn't broken yet, but it's about to. That's what basically the leak of test is telling you. Formation integrity test, I need to take it out from that list. Formation integrity test, it could be this FIT. It's a bad idea I put it there. I will take it off. Formation integrity test is not exactly leak of test. It's like I'm raising the pressure to what I think will be the highest pressure that the well will see, that section of the rock will see before I case it, and test if the well can hold that. It's different. It's a little bit different than leak of test, which is I intentionally get to the point where the well starts leaking just before breaking, and so on. So not the same thing. Any questions on how to estimate SHB? No questions. So SV is easy, SHB is harder, SH max is the hardest. Okay, is the hardest one to estimate, and many times, if you can estimate, there is a whole study to estimate the SH max in a certain location, and when you do that, it's you can write a paper about it even. It's a little bit of it's a case by case, basically. That's what I'm trying to say. It's a case by case, and you are going to see that in the first homework, which won't be posted yet. We still have some time for it. But there are several ways you can do it, but you need to see a lot of stuff. It's like solving a Sudoku puzzle. You need to look at the rows and columns at the same time, I think. Similar to here, a lot of things matter. What is the stress regime that you are in? Reverse, strike slip, normal? What are you dealing with? Blah, blah, blah. All this stuff matters. All this stuff matters. Way more challenging. You can get an approximate value working backwards if you have the fracture initiation pressure under some conditions, not always. You can use this equation, and we are going to see why. You can use this equation. If it's a vertical well under some conditions, and you have the fracture initiation pressure, you have an indication of the fracture initiation pressure, you can back calculate, back constrain SH max. The thing is, what I said earlier is that FIP, fracture can start at any point from leak of pressure to breakdown. It's a wide range. It's not a short range. So you can use leak of pressure to get an upper bound and breakdown pressure to get a lower bound. It could be a very wide range, but you can use this equation potentially, not always. For instance, not in reverse faulting, not for horizontal wells, and so on. Yeah, don't use this equation necessarily unless I suggest you to. Don't use it blindly. Don't use it blindly. That's one thing I want to say. And the other thing is, I will. You will understand. We'll come back to this equation. You will see why this equation looks like this. So you will understand the theory behind this equation. Some unknown variables in this equation. One is SH max, you know what it is. SH means you know what it is. FIP, fracture initiation pressure, which is a hypothetical value within the range of LOP and FBP. It's rare that you know the actual value. PP is pore pressure, and T is the tensile strength of the rock. Is the strength that you need to overcome to fracture the rock, to make a tensile fracture of the rock. That's the T. That's where the T comes from. Approximating FIP with the formation breakdown pressure instead results in a lower value of SH max, and then leak of pressure results in the higher value. So hopefully it's a short range, so you can stay in between. Many times it won't be. Many times it won't be. Sometimes, under the right circumstances, which we're going to see in the first homework, you can use the observation of what we call drilling-induced tensile fractures to constrain the magnitude of SH max under favorable conditions. People have done it in Australia and those areas, strike slip reverse faulting areas. And they have used drilling-induced tensile fracture observations from image logs, which you learn about in well logging, to constrain the magnitude of SH max. We are going to try to do that graphically in homework 1, which is going to come maybe next week or the week after. So I will try to delay it a little bit because it's a little bit challenging, the first one. The second homework is easier. The third one is okay. And then there is 2 more. But the first one, generally, students have some issue. They find it challenging. It's not necessarily a lot of work. But yeah, it can be tricky. You need to draw some stuff in Excel or something. Not crazy, though. Not crazy. Anyway, the students are waiting outside for the next class. Thank you, everyone. And I will see you. Have a nice weekend. And I will see you on Tuesday. Thank you very much, Michael. Good to see you.
Yep. Have a good weekend.
Yeah, you too.
Thank you.
Uh-huh.